I will talk about graphene and 2D materials and devices and sensors that we made out of them over the last years. So let's see. There you go. The most important thing is the people who've done most of the work are my group at Aachen University, but also from my second affiliation, AMO, which is a non-profit company or an institute located also in Aachen. And some of it was done in collaboration with KTH in Sweden and Georg Duisberg from Munich and others. This is the outline of my talk. I will briefly introduce material properties and fabrication procedures that we use. I will then talk about nano-electromechanical sensors made from 2D materials and optoelectronics based on mainly graphene devices. Then I will also have a few words on integration of graphene, because I believe that if we ever want to see products with graphene or other 2D materials, we have to talk about process integration with existing technology, in particular silicon technology. I mentioned that I have two affiliations, and one is the Technical University of Aachen, located at the very western border of Germany, right at the triangle of Germany, Belgium, and the Netherlands. And I there have the chair of electronic devices, which tells you the topic of my work, electronic devices. And I have about 10 members in my group there. I also, since last year, I'm the director of AMO, which is a high-tech SME, small medium enterprise, with 40 staff members. We consider ourselves a research foundry. We have a clean room of about 400 square meters that you can see here. You can see the yellow light coming out of the clean room. This is the building. And we have several key technologies. We have silicon, a silicon technology base for electronic devices, but also for photonics. We are strong in nanofabrication with electron beam lithography, nano imprint lithography, and we pride ourselves in integrating new materials into this platform. So we've worked on high-K metal gate integration, graphene, and now 2D materials. And we have applications in mind in electronics and photonics and in sensing. Now, this is the last introductory slide about Aachen. We also last year founded the Aachen Graphene and 2D Materials Center. This is a center founded by several PIs and professors from the University of Aachen, but also from AMO. And you can see the people here. Christoph Stampfer is a physicist. Joachim Knoch is an engineer working in device technology. Myself, we have Markus Morgenstern, a surface STM expert from the physics department. We also have a circuit designer. Renato Negra is an analog circuit designer, so we also work on towards analog circuits made with these 2D materials. We have Daniel Neumeier here. He's the group leader for graphene work at AMO, and another colleague, Andre Veskan, an expert on growth of 3.5, but also 2D materials. Now, I don't think the materials need much of an introduction, but I have this one slide. When we talk about 2D materials, we have semi-metals like graphene, we have semiconductors, and we have insulators. And we have typically more or less two structures. One is the graphene structure here with these hexagons, where if we have graphene, all sublattices are made of carbon, and we have a band gap of more or less 0 electron volt. If we replace A and B atoms with boron and nitrogen, we get hexagonal boron nitride, which is an insulator with a small band gap for an insulator of 5.9 eV, I'm sorry. Then we also have these so-called transition metal dichalcogenides, and one example is here. This is molybdenum disulfide, where we have a core of molybdenum atoms covered on both sides, in this case with sulfur atoms. And this material, for example, is a semiconductor, and in its single layer form, we have a direct band gap of 1.8 eV, and people have measured mobilities in this material of several hundred centimeter square per volt second. But this is not all. We have now about 2,000 2D crystals, so it's becoming increasingly difficult to choose which material you want to work with. So you have to kind of think about what properties do I like in a material, and then you can go and choose the right one. You can choose the band gap, you can choose whether it's direct and or indirect. You can choose stacks of these materials, which then also alter the properties. And I would like to say that it's probably not fully understood what happens when you place two or more different materials on top of one another. So there's still a lot of basic fundamental research needed to move this forward. Now, in Aachen, we've decided, or at least in my group, we've decided to work mainly with scalable technologies. So early work on these 2D materials is typically done by exfoliating, where you take a crystal and you peel off these monoatomic layers, and then you work with these so-called flakes. In our case, we like to work with large-scale materials, so we like CVD fabrication methods. And here's the example of graphene, where we typically take a metallic surface, a catalytic surface. In our case, we like to use copper, and we use CVD, thermal CVD, or plasma-enhanced CVD methods to grow from a gas phase, from methane in this case, monoatomic graphene layers on the surface, and then we transfer them. And this has the advantage that it's large scale, and we can do this on a wafer scale even. On the other hand, we have to transfer the material, and this is still problematic because it's a manual process and it introduces a lot of defects. Now, we can also grow 2D materials with this kind of method. In this case, I'm talking about thermally assisted conversion, which is a derivative of the CVD method, where we start out with a metallic surface and then we introduce a material. In this case, the metallic surface is platinum, and we introduce selenium, and then it intercalates and it forms these layered 2D materials. And this is typically done at temperatures between 400 and 800 degrees C. The nice thing about this platinum diselenide, and that's why I chose it, is that it can be transformed at 400 degrees C. This makes it compatible with back-end of the line CMOS processing, and so it could in principle be integrated after making a CMOS circuit, and it wouldn't destroy the functionality of the CMOS, and you would then add this functionality due to the 2D material. You can see a TM image here. You can see the nice layered structure of the platinum diselenide. This was grown actually at my friend Georg Duisberg's lab in Dublin. So this is the Raman spectrum. I'll skip that. And then what we typically do, we take these materials, we transfer them, and we make all kinds of devices. We make DC and RF transistors. We make optoelectronic devices and NEMs, and I'll talk about these too. And the nice thing is these thin materials are also very flexible, so we also look into flexible electronics. This is a flexible photodetector, and this is a flexible Hall sensor. Now, why would we use 2D for MEMS? And this is something, so I have some of the properties summarized here. For graphene, the Young's modulus is extremely high. For other 2D materials, it's lower than that, but it's still quite high. These materials are piezo-resistive, so we can use them as transducer materials. The gauge factor of the 2D materials can be between 50 and 100 or even more. They're flexible and stretchable by up to 20% in the case of graphene. They're mechanically stable, they have a low mass, they have a high surface to volume ratio. So all these properties say that, or indicate that the materials should be good for 2D based mass, force, pressure, gas, or biosensors. So all kinds of sensors should be highly sensitive when we use these materials. And this is one of the earlier works we did in Aachen with the Morgenstern group. We looked at graphene on a silicon oxide surface. And when you put graphene on a silicon oxide surface, it is corrugated. And the roughness of the silicon oxide and the corrugation in the graphene lead to natural nanomembranes that can occur randomly on the surface. And in this case, they identified here with their STM a nanomembrane with a diameter of about 5 nanometers. And then by changing the tip distance, they were able to actuate this membrane and extract parameters, the material parameters. And then by using the clamped membrane theory, they concluded that actually this nanodrum should have a resonance frequency of about 400 gigahertz. And they confirmed this with molecular dynamics calculations. And what that means is that it should actually be, this membrane should be able to detect the presence of a single hydrogen atom attaching to its surface. So it would be an extremely sensitive mass sensor. Now, of course, this was not the direct proof that it works. It is a long way until we get there, but at least this is the potential of the material. We tried to use graphene also in a different way. We figured that if we strain the material, we will the theory predicted that you could get band gaps in the material up to 1 eV. Turns out that you have to strain them quite a lot to get there. And in our device configuration, we never got to these large strain numbers. However, even a small strain will shift the drug point and change the density of states, the mobility, the charge carrier density. And so at the end of the day, straining graphene will change its resistance. And this is what we try to use in a device where we had a cavity here, and we had a pressure of 1 bar trapped inside. And then by changing the pressure on the outside of this cavity, the graphene membrane gets deflected. And because it's piezoresistive, we can measure this directly. So we have a membrane that is ultimately thin, and it acts at the same time as the membrane and the transducer material. And well, we did this for round membranes where we have more or less radial or a biaxial strain, and then we also did this for very long, very wide and narrow membranes where it's uniaxial strain. And at the end of the day, we were able to measure with these membranes, this is the pressure, this is the voltage across the membrane, and you see the piezoresistive effect here. The resistance changes as a function of pressure, which means the deflection of the membrane and the strain in the membrane. And the red curve here is actually a reference patch of graphene without a membrane. So you see there's no signal here. We also then calibrated this to the size of the device and compared it with state-of-the-art technologies. And because the membrane is so thin, we actually get very, very high sensitivity per unit area. And you can see that here, the graphene is normalized to 1, and then we get 5% or less for existing technologies with this normalized sensitivity. And this all despite a low gauge factor of around 3 for graphene. This is actually not a high number. This is almost like a metal. It's not surprising, it's a semi-metal. But at the end of the day, the thickness or the thinness of the membrane, which is only 1 atomic layer, so it's less than a third of a nanometer, makes it very size scalable. So we also did this with the platinum diselenide, and here the gauge factor is -85. So at the end of the day, this material would be an even better strain sensor. And again, the sensitivity is already better than even commercial products, which are optimized for sensitivity. But then if we normalize this again, the advantage is at least 2 orders of magnitude. And then we had this one champion device, which we don't fully understand yet, but it survived for a long time, and it always went back to these good numbers. So we get this extremely high sensitivity for the platinum diselenide. So this is work going on, and it's under consideration. So hopefully we'll have more time to work on this in the future. Now, talk about metrology. How do we know that we have membranes that are intact? And for this, we use Raman spectroscopy, and we can do area scans where we see this is a defective membrane. There's a small defect here. This one is non-existent. And then here the yellow cavities are covered with graphene. So with Raman spectroscopy, we can clearly distinguish that and see that. And then we also went and did some 3D imaging, and we did depth cuts of these devices, and then we can reconstruct even a 3-dimensional form of this device. And this is what we call 3D Raman tomography. And this is a nice way to investigate NEMS devices, even though the Z resolution is not very good. But for our purpose, this was very nice. And we also applied this to the platinum diselenide, and you can see here this membrane was intact, and we were able to measure it, whereas this membrane collapsed and was attached to the bottom of the cavity. So this 3D imaging with Raman spectroscopy is a good way to check these membranes. Now, this was the part about MEMS. Now I will talk about optoelectronics. And graphene is an interesting optoelectronic material because the dispersion relation is linear up to about 1 plus minus 1 eV. What this means is that you can shine light of any wavelength onto the graphene, and you can create electron-hole pairs. So it's a very wide bandgap material. In fact, it goes from the UV visible even to the terahertz range, and we'll hear more about terahertz and graphene in the next talk. It has very high carrier mobility. So once you generate these electron-hole pairs, you can extract them very fast. So we can get very high data rates with graphene photodetectors, and and it's broadband. So this is the motivation why we would look at this in the first place. Some early work I did when I was still working in the US was this here, where we looked at scanning photocurrent measurements of graphene. And so we made a device with a top gate here and a bottom gates, and this is the blue area is the graphene. And then we looked at, by mapping, by scanning a laser beam across this whole surface, we looked at the active areas. Where was the most photoactive region? And it turns out that it was close to the contacts and close to the gates. And by changing the back gate and the top gate, you can play around with the carrier density in the graphene and the carrier type. And at the end of the day, we established that probably it's a photothermoelectric effect, where the Seebeck effect comes in here, because that changes strongly when you change the polarity. So when you have a PN junction in the graphene and you have that near the top gate contacts, in this case, you get a strong photocurrent. The disadvantage here is the low overall responsivity. You have to think about, this is a monoatomic layer of graphene. You shine light vertically, and you only absorb 2.3% of the light. So it's not a very efficient photodetector. So to be more efficient, you have to do something else with it. And we started doing this by integrating graphene with silicon. And here we have 2D, 3D co-integration. Basically, we have a silicon substrate. We put a graphene patch on top, and we contact the graphene and the silicon, so we have a Schottky diode, because graphene is semi-metallic, and if we choose the right type of silicon, we can get a Schottky barrier. And this is the top view, and then this becomes the active area of our diode. And you can see if we use P-type silicon, it doesn't show very much rectification, but if we use N-type silicon, it's very clearly a diode. And that has to do with the fact that graphene gets P-doped when it's in air. So this is just an ohmic contact, whereas here it's a Schottky barrier. And then we can extract the ideality factor and the barrier height, and which we did, and so on. So this is the spectral response of this diode, and you can see this is the wavelength, and this is the spectral response in milliamps per watt. You can see this strong response here, which happens to be the response of the silicon. So we're really detecting here in the silicon. And we compare that to a commercial Hamamatsu diode. The shape looks pretty much the same. Hamamatsu diodes get about 500 milliamps per watt. With this one, we get about 250, so about 50% of the commercial diode. But we also, if we look into the infrared region, we also see a bias-dependent photoresponse here, which is about 1 per mil of the original response in the top response in the silicon. But this is the graphene actually absorbing in the infrared. So we do see some tail here, but it's 1 per mil of the original signal. So again, it's very weak because we come from a vertical direction. Now we've looked at this in more detail, and we found actually when we do another scanning photocurrent measurement of this diode, we see that for small bias, the main photocurrent comes from the Schottky region. But if we go beyond a certain threshold voltage, the main contribution actually comes from this region here, which is on the silicon oxide. And that's kind of surprising, because we would expect this region to be active and this to be passive, but that's not the case. Because we shine through the graphene and the silicon oxide, we still excite carriers under the oxide, and due to the oxide passivating the surface, we actually get very little recombination. This is our theory, at least. And so the carriers that are generated here can go under the oxide and then come back and get to this gold contact. So by doing this, we're now able to make very, very efficient photodetectors that actually work better than pure silicon commercial photodetectors if we optimize this ratio between, oxided area and non-oxided area. And this is work in preparation, so hopefully I can talk about it more in the future. Here we go. We also did similar diodes with platinum diselenide. Again, you see the silicon signature here. Again, in the infrared region, you see the absorption, because platinum diselenide is also a semi-metal. And here we get actually several, or up to almost 2 milliamps per watt, depending on the thickness of the platinum diselenide. So again, we can make photodetectors that work in the infrared with bad efficiency, but I think it's still an interesting thing to look at in the future. Yes, we also made flexible photodetectors, and this is an interesting point where we made devices from amorphous silicon, and here we made a PIN diode. And the intrinsic region here is interesting because we tuned it by adding carbon and by adding germanium to the material. So we have now a band gap that is variable across this PIN junction. And because the penetration depth of the light is different for different wavelengths, and then also we can bias this differently. We can extract carriers from certain regions preferentially by applying different bias voltages. So we can actually, by running an algorithm, we can actually make a photodetector that is multispectral. We can detect the color with a single photodiode. And the graphene here is really only a transparent conductor. But what it does, it adds flexibility, because the amorphous silicon is somewhat flexible. The graphene is very flexible, but conventional transparent conductors are usually very brittle. So now we can make these multispectral photodetectors, and we can make them on flexible substrates. You can see this is bended here. This is the dark current. This is the light current. And so this is something towards, let's say, flexible electronics that we can do. I'll skip this slide. Now, finally, I would like to spend a few minutes on graphene silicon photonics integration, and this is work done at AMO over the past probably 8 years. We can make phase modulators. I won't talk more about that. So that we have the silicon waveguide here, and we can modulate the phase of the light. We can detect photocurrents. We can detect the current in here and transfer the signal from an optical signal into an electronic signal. We can make variable optical attenuators. We can make very, very efficient heaters out of graphene. And we can make an absorption modulator. So we can modulate the light with the graphene by applying certain biases. And I will just pick the two examples of the photodetector and the modulator. Now, the modulator works in the following way. I said you can detect light of any wavelength, but that's only true if the Fermi level of the graphene is below half of the wavelength of the light. Because if you go beyond that, if you just turn the Fermi level larger than half of the wavelength, you actually block the states. So there are no available states, so the graphene actually becomes transparent. And this is a simulation here on the right-hand side. You can see here the absorption going down as a function of the chemical potential of the graphene, and this is half the wavelength of the light. So that's where they have this large drop-off. And this is one thing. You can also use the same configuration where you have the waveguide here and you have a graphene layer close to it. And then in this region here, you can actually also do phase modulation, but I don't have time to talk about the mechanisms there. So the device we made was the following. We had a silicon waveguide. We had this absorption layer here of graphene in black, and we had a second graphene layer to gate the first one. So we can apply a bias here. This will gate the lower graphene layer, and that way we can tune the Fermi level of the lower graphene layer. And these are just some technical parameters, but the measurement is actually here. You can see this is transparent. The transmission loss here is about minus 14 dB overall. You have the light coming in here. You have the two graphene layers. And then if we apply more than minus 10 volts to the top graphene, we actually turn the Fermi level, tune the Fermi level in lower graphene, and we absorb the light here. Now these detectors, when you compare them with the state of the art, we have modulation and attenuation, and we get the modulation over the attenuation here, which is better than existing technologies. We also, at least in theory, have a very good bandwidth that exceeds that of germanium photodetectors. So having these detectors or modulators can be very efficient. Now I'm talking about the photodetector. This is where we drive or we keep the Fermi level sort of centered in the graphene so that it actually absorbs photons always. And here we did this integration also. Here again in a waveguide, and went to very high frequency to measure this. And all this was done on a 6-inch wafer where we placed graphene at certain strategic points where we wanted it to be. Now this measurement here is the RF response measured up to 130 gigahertz. We show data transmission at 50 gigabit per second. So these numbers are quite good. Is it 25 minutes now? Or? Yeah. Okay, so I'll hurry up. In any case, you can see here also the open eye diagram at 12.5 gigahertz that we measured. And then we couldn't go further because the measurement equipment was at its limit. So I'll skip this slide. And so this is just an overview of how we do this. We simulate, then we make our photonic structures on a wafer scale, then we integrate the graphene on it, then we measure it on chip, and then we can also package this. And this was shown last week at the Mobile World Congress, a 25 gigabit per second transceiver using silicon photonics and graphene photodetectors. And we're hoping to work further on getting this to a high technology level, hopefully to be able to sell it even at some point. I mentioned the 6-inch wafer processing, so we work together with a company, Graphene, who are making wafer scale graphene, and they have a professional transfer process, so we can make now 6-inch processing. The entire wafer is covered with a graphene. It's a semi-automated processing. It has high yield. We can make standardized chips and customized processing. Of course, variability, reliability with graphene is still an open question, but we need to move to wafer scale processing to get good numbers of this. And finally, I mentioned the collaboration with our analog designer in Aachen, Renato Negra. We made a MMIC process with passives and also active devices. The active devices can be diodes. I didn't mention them in detail, but also graphene field effect transistors here at this layer. And then we can also do encapsulation, capacitors, inductors. And using this MMIC process, here's one example. We made a Wi-Fi 6-port receiver front end on quartz in this case. We can also make this on flexible substrates. So we now have the sensors, we have the optoelectronic devices, but we also have circuits based on graphene that will able to allow us to do on-chip data processing, at least analog processing, and then even transceivers that work at baseband frequencies. So we made 2.4 gigahertz transceivers that can actually be used as Wi-Fi data transmission for these, let's say, flexible graphene-based or 2D-based systems. So this is the end of my talk. I talked about graphene 2D NEMs and why graphene resonators should have record performance and 2D membranes in general as pressure sensors with very high sensitivity. I talked about optoelectronics. The reason for the photodetection in graphene is the photothermoelectric effect, we believe. I've shown heterostructures, integrated 2D and 3D materials to make high-performance photodiodes. And I also talked about graphene for PICs, photonic integrated circuits, where we have modulators, high-speed photodetectors, and other devices that we can now also integrate on the wafer scale and in the future integrate with analog integrated circuits to also do data processing on chip. And with that, I would like to thank you for your attention.